Hey there, welcome back to 2241. Today we're going to cover motion in space. This is a relatively short section, but it does have some complex problems in here that we need to go over. All right, so first off, we have some terms here, and I'm actually not going to cover these on the next page because they are essentially the same concepts that we already know, just reskinned as physical things. So I'll go over these, at least velocity vector, speed, acceleration vector, Newton's second law, and then the tangential and normal components. So I've labeled things as velocity vector and speed, and then vector and so on, because we need to keep track of which things are vectors and scalars in this section. All right, so as far as our formulas go, we have our standard position vector, r as a function of t, with three components, x, y, and z. And then the velocity vector is defined as the change in position over time. And so you have the standard difference quotient here with your position vector, and thus the velocity vector is actually the same as just the derivative vector of r. It's the tangent vector at a point. The speed then is the magnitude of the velocity vector. It's how quickly you're traveling, how long that derivative vector is. The acceleration then is how quickly the velocity vector changes, and that should have a prime on it. And then the second derivative of position, as one might expect. And then here we have Newton's second law. So you may or may not have seen this before, but what it says is that if you have some object with a mass m, and it is accelerating in some direction with some size, then there must be some force acting on it that is equal to the sum of all smaller forces that are acting on it. So if you find that maybe there's a baseball traveling through space and it's being acted on by gravity, then you'd only have one force here, and it would just be the gravitational force, and it would be equal to the mass times the acceleration of the object. And we happen to know the acceleration at the surface of the Earth is g. So there's an example of Newton's second law in action. The other things that we have are projectile motion, the equations for this. These are a little bit more complicated, and we'll derive these in a problem later. But I just want you to see them. Note that y has a quadratic component here, whereas x is purely linear in the time variable. And then that's what these all mean. So t is time, v0 is the launch speed, not velocity. So this is just a scalar. Phi is the launch angle. So if you launch something at an angle of phi with the ground like this, then phi is that angle. And then g is the gravitational acceleration. So this is the acceleration for us at the surface of the Earth. In most applications, g equals 9.8 meters per second squared. Of course, if you're looking at projectile motion on the moon or on Mars, then this might change. Okay. And last in our formulas is the acceleration in the TNB frame. So it has components along the tangent and normal vectors. And the acceleration will actually not have any components along the binormal vector. And that is specifically because the acceleration and the tangent vector define the osculating plane of a space curve at a point. So if you think about maybe the derivative of the acceleration, that will be proportional to the binormal vector. But we don't see b show up for the acceleration. Okay, and so we have this general formula for the acceleration. This is it written a little bit more nicely without the t's. And then the tangential components are just the numbers, the scalars that appear in front of t and n. So v prime and kappa times v squared. Note the normal component depends on the curvature here, as well as the square of the velocity. So those are some interesting dependencies. And we have these simpler, or maybe in terms of simpler quantities, formulas for both the acceleration in the tangential and normal directions. And these are similar to things that we've seen before. Okay, so those are our formulas. We have some extra things here in the formula section. I do not need you to remember these, but they are there as extra information. Kepler's laws, and I'll read them off for you. Kepler's laws say that planetary motion is elliptical. So if I draw the orbit of a planet, it should look something like that and not like that. So circles are a no, ellipses are a yes. The speed of revolution is proportional to the area swept out by a line segment between a planet and the center of orbit. So if we have an ellipse like this, say this is the orbit of the Earth around the sun, it's kind of exaggerated here, then if we draw the Earth blue, maybe right there, and the sun is down here, then let's say we draw a ray between the Earth and the sun, and then we draw the Earth sometime later, right? Then there's an area between these two rays. Okay, well, then let's say we measure the Earth at some other position, and then a later time, maybe here. Well, these are definitely very different looking shapes, but if this delta t right here is the same as this delta t, then let's call this A1 equals A2. And that's if these are both delta t, same amount of time to go across those two arcs. All right, last is that the orbital period of a planet, that's the time it takes to go all the way around the orbit, is proportional to the 3/2 power of its maximum orbital radius. And the maximum orbital radius is the distance from the center, so the sun in this case, to the what is that called? I think it's the perihelion of the orbit. Note that actually the sun is not at the center of the Earth's orbit. It's at a focus of the ellipse. It has two. The ellipse has two of those, and the sun is at one of them, and the Earth orbits around like that. So I just used the sun in the center as a pedagogical example there. Okay. Last is our objectives here. So as usual, easy, medium, hard. One, I want you to recall the formulas in this section. When you're doing sort of physical stuff like this, it's really helpful to just have those in the back of your mind. I want you to understand the physical significance of the formulas. So what does the acceleration vector mean? Velocity measures what sort of quantity? How do I draw in the tangential and normal components of acceleration? Those sorts of things. I also want you to be able to compute with these formulas, so use them, plug in some numbers, and get out the right answer in both simple and now medium complex cases. So medium objective, compute the formulas for complex cases. And then the last medium is I want you to set up problems given physical descriptions. So often a problem will be described in plain English, maybe they'll give you some parameters, and you have to turn that into a problem in mathematical language that you can then solve. All right, for our hard objectives, I want you to be able to use knowledge of vectors, all of the stuff that we've learned already, to interpret the results of a problem. So maybe you end up with a quantity that you don't know by heart or off the back of your hand. You've never seen the result here before and you don't know what to do with it. Well, you can use what you know about vectors sometimes to interpret those results and give them a physical description. So something like the derivative of the acceleration vector, that might correspond to a certain kind of motion, maybe like a cubic type motion. And you should be able to use your knowledge of vectors to figure that out. Last is derive and apply Kepler's laws of planetary motion. Again, I said that I don't need you to do this, but it is a hard objective if you want to get really, really good at this sort of stuff. All right, and that's going to be it for our overview. Like I said, it's a short one, and we'll cover examples in the next section.